All right, let's get right into it. Today, we're going to break down a really important concept in algebra, improper algebraic fractions. Ever seen one of those fractions with polynomials that just looks, well, top-heavy? If you've wondered how to wrestle those into something simpler, you are in exactly the right place. We're going to walk through the main technique and solve some classic problems.
So, here's the game plan. First, we're going to build a bridge from simple number fractions, stuff you already know, to these bigger algebraic ones. Then I'll show you the one master tool you really need to solve these, polynomial long division. And finally, we're going to get our hands dirty and solve the exact kinds of problems you'll see in your textbook.
Okay, let's dive in. Before we jump into the wild world of x's and polynomials, let's ground ourselves in something we all get, simple numbers. This right here is the whole secret. Look on the left, 11 over 5. We all know that 5 goes into 11 two times, with 1 left over, so we write it as 2 1/5. Now look at the beast on the right. I know it looks way more complicated, but I promise you it's the exact same idea in a different costume. Our whole goal is to pull out the whole part, the polynomial, and see what little fractional part is left over. So what's the official rule? What actually makes one of these things improper? Well, it's all about a power struggle between the top and the bottom. You just look at the highest power of x in the numerator and compare it to the highest power of x in the denominator. If the top's power is bigger than or even equal to the bottom's power, bam, you've got yourself an improper fraction. That's always the very first thing you check.
Okay, so we know what they are, but how do we actually, fix them? How do we split them up? Well, we're going to pull a tool from way back in your math toolkit and give it an algebraic upgrade. I'm talking about long division. Yep, that's right.
The whole method is just a simple four-step dance that you repeat over and over again. It's divide, multiply, subtract, bring down. That's the rhythm. Just keep doing that loop until you can't go any further. So, enough talk, let's see how this dance actually works with a real problem.
All right, time to put this into action. We're going to tackle a question straight out of exercise 7a, and this will make that four-step process absolutely crystal clear. Here we go, we're jumping in with question 1c. We've got 4x cubed minus 3, and we're dividing that whole thing by 2x plus 1. The mission is simple. Break it down into a nice, clean polynomial and whatever little fraction is left over at the end. First things first, setting it up. And hang on, because this is probably the single most important tip I can give you. Look at that numerator, 4x cubed minus 3. See how it jumps from the x cubed term straight to the plain number? It's missing an x squared term and an x term. If you just dive in, your columns are going to get messy, so we add placeholders. We rewrite it as 4x cubed plus 0x squared plus 0x minus 3. Trust me, this is a total lifesaver.
All right, first lap. Remember the cycle? Step 1, divide. We take the front runners only, 4x cubed divided by 2x. That gives us 2x squared, and we pop that right up top. Now, step 2, multiply. We take that new answer, the 2x squared, and we multiply it by the entire divisor, the 2x plus 1. That gets us 4x cubed plus 2x squared, and we line it up neatly underneath.
And on to the back half of the loop. Step 3, subtract. Now be careful with your signs here. The 4x cubed terms cancel out. That's what we want. And 0x squared minus 2x squared leaves us with a negative 2x squared. And finally, step 4, bring down. We just grab the next term in line, which is our 0x placeholder, and pull it down. And look at that. We have a new expression, and we're ready to start this cycle all over again.
So we just keep running that same loop a couple more times until we get to a remainder that's too small to be divided anymore. And that's it. Our final answer is the polynomial we built up top, 2x squared minus x plus a half, and then we just tack on that final remainder written over our original divisor.
Awesome. So now you've got the core technique down pat, let's switch gears just a little bit. The next few questions use the exact same skill, but they frame the problem a bit differently. This time, they want us to find these mystery coefficients, the a, b, and c values. So check this out. For question 2, they basically give us a template for the answer. They're telling us, hey, your answer is going to look like this, sum ax squared plus bx plus c with a remainder d. All we got to do is the long division, just like before, and then play a little matching game to find out what a, b, c, and d actually are. Okay, so we just do what we do best.
We set up our long division, and yup, don't forget that placeholder for the missing x term, and we just run through our cycles. When all the dust settles, we end up with x squared plus 4x plus 12 as our polynomial, and a nice clean remainder of 29.
And now for the easy part. We just line up what we got with what they asked for. Our result was x squared plus 4x plus 12 with a remainder of 29. Their template was ax squared plus bx plus c with a remainder of d. So by just matching the terms, a is clearly 1, b is 4, c is 12, and the remainder d is 29. It's really that straightforward.
All right, next up, question 3. This one looks a little bigger. We're starting with x to the power of 4, which just means there's an extra coefficient to find and maybe one more trip through our 4-step cycle. But, and this is the key thing, the method is exactly 100% the same. No new tricks needed.
So, after you crank the handle on the long division machine for this one, you get x cubed minus x squared plus 6x minus 6, and you're left with a remainder of 5. Then you just match them up to the form they gave you to find a, b, c, d, and e. Same game, just a slightly bigger polynomial.
Okay, last one, question 4. This one has a fun little twist. Take a look at what we're dividing by. It's a cubic polynomial this time. Now, your first thought might be, oh no, do I need a whole new method? And the answer is a big, resounding nope. The beauty of this method is that it doesn't care. Our trusty 4-step cycle works no matter what.
And what's funny is this division actually ends up being a bit quicker. We get a simple polynomial, just 2x plus 3, and our remainder this time is a linear expression, negative x plus 6. So we compare that to the format they want, and we can just read off the answers. A is 2, B is 3, C is negative 1, and D is 6. All done.
So, there you have it. We've walked through the mechanics, you've seen how to solve the problems, you've totally mastered the how. But I want you to leave thinking about the why. Why do we even bother with this? Because this skill, this isn't just a trick for an exam question. This is a key that unlocks much bigger, more complex problems down the road. When you get to things like calculus and need to use a technique called partial fractions, this will be your crucial first step. So what you've really learned today isn't just a procedure, it's a foundational tool for your entire math future.